Thank you, everyone. Welcome back for session 3. It's my pleasure also to say thank you to Sequent and Mix Deposit, and they also have Leapfrog in their system now for sponsoring this session. And I'm also now going to introduce Dr. Tony Webster to give us a presentation on structural data, and then we're going to follow that with Dale Sims, and he's going to talk about 3D modelling. So I'll hand over to Tony now. Thank you.
Okay. Hopefully the microphone working. Can you? Right. Okay, I've gone remote. Right. Sorry, just checking the tick. Move this position. Well, hello everybody. I'm hopefully going to get through a very large number of slides today, but I'm also hopefully going to try and convince you that structural geology is not scary. I may not achieve that with the number of slides I have, but that was my hope when I started putting it all together. But basically what I want to try and do, unfortunately my slides are very wordy. I'm working on the basis that because this is being recorded, I'll have to gloss over a lot of the text, but if you're reviewing the recordings, if you wish to, of these, you'll be able to stop these things and see I've probably packed a lot more stuff into these lists of words than I probably will actually talk to. But you can stop the video later on and read kind of what I've put in. That's kind of the theory. Whether it works out as a fact's another matter. So what I want to try and do is talk very briefly about the most common sources and types of structural data, and that's going to be very brief. A very brief overview of how it's collected and presented and interpreted, but what I really want to talk about is the next step. The less common sources of data. That's really what I'll be focusing on. And then I'll talk about a few case studies or a couple of case studies where it's really what you do with this data rather than how you collect it. And then maybe I'll get a chance to give you this big list of some of the problems you can encounter with structural data, but mainly fairly minor things, but I just thought I'd better put that in. So this is the area I want to focus on. The less common and not necessarily obvious sources of structural data that you might encounter on a project that maybe doesn't have the world's greatest database of drill holes. And it's very much my personal view. So it's not what you will read in some of the famous structural geology textbooks like Hobbs, Beans and Williams. It's kind of what I've found to be really useful. And in kind of, I do a lot of work in mining. That's where I earn my living, in mining problems, but also a lot of brownfield stuff. And I seem to have spent a lot of my career working on historic mining fields like Broken Hill, Kalgoorlie, even on the west coast here on Hercules, and those sorts of places. So I've kind of spent a lot of my career working with non-drilling data and stuff that started off as paper or mine plans and things like that. So I thought rather than just give you Geology 101, alphas, betas, orientated core and all that stuff, I'd gloss over that and move into the stuff that isn't going to be in a YouTube video. So, and it's very much kind of what I do. My cursor's not going to show up for the electronic people, but I'll try and point at things. That's why I've got this thing on. Very much my point of view. Now, when I was doing a bit of a review of what project geologists actually do according to Seek job adverts, it seemed that most of a project geologist and above has moved away from being a field data collector to being more of an interpreter and a manager of the people that collect the field data. Trainer, mentor, leader of teams, planner of the next step in the process. So that's the sort of stuff I thought I'd look at. So basically what that means is you stop collecting alphas and betas for your entire life in the core yard, hopefully, and you've moved on into interpreting the fun part of it sometimes to actually work with that data. That's the assumption I've based this on. So let's get into it. I had to put in a little tiny bit of background information. I wasn't going to give you Geology 101. You should know all that stuff by now, but I did think I'd just remind you about stress and strain. Stress is the forces acting on a rock, and strain is the effect of those forces as the rocks change as a result of those forces. So if you put stress on a rock and it breaks, the breakage, the fault, is the effect of the strain, is the sign of the strain, but stress is the force acting on the rock. Not that I'll talk about this stuff much. There's two major types of deformation we talk about. There's ductile deformation. That's basically where the rock moves mostly from an element of recrystallization and movement, an element of recrystallization. It can even be kind of almost a plastic flow, or brittle or cataclastic deformation where the rock breaks. So the difference between basically a shear zone, which mostly moves by recrystallization, compared to a fault zone, which might just break and crumble and you'll get gouge and all sorts of things inside the plane of it. So brittle and ductile, I won't talk about that much. I just thought I'd chuck in a bit of terminology. But what are we using structural data for? So really what we're using it for is it puts the third dimension into our interpretations. So you can map the geology underground, you can map the geology at surface, and you end up with pretty much a two-dimensional representation of geology. But if you can actually start to predict, if you can actually measure features of the rock that allow you to say that it's dipping at 45 degrees to the northeast, you can start to actually put the third dimension into these representations. And that's really what we're doing. And up until the invention of computers and these powerful modelling software packages, we were mostly doing that using traditional mine plans like cross sections, level plans, longitudinal sections, all these sorts of things you'll always find on a historic mine site, but you don't see so much now anymore. But I'll be talking a lot about how you can use some of those plans later on. So we can get measurements that will give us the orientation of planar features, their dip and their dip direction. We live in a world where computers tell us so much about what we do. So we get taught to measure dips and strikes at university, but the software packages can't really cope with strike. So most software packages like to have dip and dip direction. So we talk about that. So that's why we still don't really often measure dip and dip direction. We still want to do dips and strikes in the field because that's what we're taught at uni, I guess. But really the software packages want dip and dip direction. And we can do plunge angles of linear features. That's the angle from the vertical of a linear feature and the direction it's plunging towards. So that's really what we're adding to the geological interpretation, and that's really what structural geology is for. And we care about these things because the rocks that host the mineralisation, if we know their orientation and their geometry in 3D, and they're hosting the mineralisation, then it tells us more about the geometry of the mineralisation. And also, if we understand the geometry of features that break those rocks that host the mineralisation and move them relative to one side or the other, like a fault, then we need to understand the orientation of those features as well. So, but also one of the sort of the area I've worked in more really a lot for the last 10 years is I suddenly got turned around from worrying about the ore bodies to worrying about the wall rocks, because I kind of got into the, not geotechnical sphere, but I started working a lot with geotechs, and I started to worry a lot more about not what the ore body was doing, but what happens to the rocks hosting the ore body in the walls of stopes and open pits. So that's a really important area that we need to understand too. So you probably don't care much about that if you're doing exploration, but you care an awful lot about that if you're working on a mine or on a feasibility study of a project that's going to become a mine. You start to really care about the wall rocks. So you sort of have to turn yourself around and think about the mullock as opposed to the ore, which can be kind of hard to do because it's not as sparkly and bright often as the ore itself. And the structural data allows you to analyse geometric relationships between the different sorts of structures that you recognise, that you can see. And I'll talk about that a little bit more in a minute. And I've kind of made this point, but if you don't have that third dimension, you're really kind of just joining the dots on cross sections and plans. So that's really what structural data is doing for us. It's adding that third dimension to our interpretations. I've said a lot of this already, but what we're trying to achieve with structural data is understand the controls on the location and geometry of mineralisation, or the rocks that host it, the relationship between the ore and the mineralisation itself, the mineralisation or the ore and the strata and structures that host it, whether to ask questions or answer questions like, is it strata bound, is it strata form, or is it completely outside the history of the rocks? It's just come in as an event, so it's epigenetic, it's formed later than the rocks that host it, and it may not have a geometric relationship to them apart from maybe being hosted in a fold hinge or something like that. We want to know about the geometry of structures that host the ore, so say high-grade mineralised chutes in a lode system that tend to have a plunge and a plunge direction. I've already said this, but you want to know the geometry of the structures that dislocate the ore, the orientation of linear features like folds that might buckle the ore. And you want to understand all these features so that you can actually predict, especially in a near mine or in mine exploration environment, to identify the positions of potential new ore or mineralisation. I originally had a slide where I was going to talk about micro, meso and macro scale, but I left meso scale in because really when you're working in a mine, you're talking about mesoscale, middle scale structures, because you're interested in understanding sort of a stope scale or mine bench scale or high wall scale, what the structures are doing, as opposed to regional exploration where you're talking about mega scale structures quite often and trying to zero in on a target like Kate's just told us how you do, but with geophysics. But you might be in an area where it's multiply folded and you're looking for perhaps repeats of particular structural positions that you might know hold host mineralisation, like saddle reefs in Bendigo and that type of thing. So that's kind of what we're trying to achieve with it all. I've already said a lot of that. A sphere that I work in an awful lot at the moment, and some of you guys are involved in feasibility studies for this thing, these sorts of things now. If you're involved in a block caving or a sub-level caving feasibility study, or even an operation, like some people I was just talking to a minute ago are kind of, you need to understand the structure of the rock mass, the host rocks, for about a dozen different reasons at early feasibility to pre-feasibility stage to actually have any hope of so much of the work in a block cave where there's no underground development to speak of is done by numerical modelling, by very clever software packages that take the structural data from drill core, it's nearly always drill core because there's no underground development, hardly any surface exposure, a lot of these things, and that's used to underpin basically every decision that's made about a block caving operation, for everything from the development orientations for undercuts and extraction levels, all the way through to the size of blocks that will form when the rock's failing under its own weight, which is the way block caving works, because you want to know how big the blocks are going to be so they don't clog up all your draw points at the bottom. If you make the draw points too small to get the blocks of ore that have naturally failed in the subsidence column out the bottom, then you can't draw the ore out. So all the information that allows you to do that in a block caving feasibility study is, nearly all of it, is structural data from drill core. Everything from veins to everything else. So it's become much, much more important in a way in the pre-feasibility stage rather than just managing the ground conditions in operating mines that we're kind of mostly used to, particularly in the Australian industry, and as mines are getting deeper. So in mining, I'll keep jumping ahead of myself in a way, but in mining, what's structural geology for? It's really about managing ground conditions, predicting bad ground, monitoring the ground conditions around stopes so that things like this don't happen. It's an old website that used to get some great photos from called Mining Mayhem. I don't think it's alive anymore, that website. But also the structural geology data that we collect as particularly mine geologists is also, it underpins what the geotechnical engineers are using. It's the structural model that they use to manage the ground conditions and predict ground conditions in mines. So basically structural data and the structural models you build from them underpin geotechnical management of mining operations. Everything from the high walls of giant pits to to the hanging walls and footwalls and development ends of underground mines. And you also need to have some accurate information about the physical properties of the rock. It's not just how the rock's going to bend and break. It's also about how hard it is and how soft it is, and whether it's going to generate fines in a block cave or whether it's going to form big blocks, those sorts of things. So you need to understand some of the physical properties as well. Anyway, and you need to understand it to manage groundwater, particularly in big open pits. The structural model is usually the foundation for a hydrogeological management of mines, so that it basically it underpins dewatering, keeping the working areas dry, and particularly managing the water, the dewatering of high walls and pit faces to prevent pressurisation, the pressure of water building up behind and causing failures. So structural data and models underpins all that too. Right, the most common forms of structural data. This is what I'm not going to talk a lot about, but there are really sort of three categories of structural data. A lot of this is written off the top of the head for me, but there's direct measurement from outcrops, which we were all taught to do at university, the old compass, tip and strike, pretty fundamental tool, still used everywhere. Then there's the direct measurement from drill core, where you can use these funny little instruments that people tend to call rocket launchers, where you can actually, they're a framework that's on a rotating base and it has a tilting angular rack where you can put a piece of drill core. If you know the hole's been surveyed and you know the dip and the dip direction of the drill hole, and you're looking at a particular depth where you know the dip and the dip direction of that drill hole, you can actually set the frame up to the original orientation of the drill core, put the core on it with the down hole mark on it, which I'll talk about in a sec, and directly measure features of it. Now, some people really like doing that, but then more recently, I guess in the last 20 or 30 years, which is not that recent, it is for us older people, you've got these canometers and goniometers, these frameworks where if you have an orientation mark in the core that shows you where the bottom of the hole is, you can orientate them so that you can actually do two measurements, an alpha and a beta measurement, which allow you to calculate the dip and the dip direction of the feature that you've measured in the core. Now, as I said, I'm not going to talk about this stuff much. This is, like I said, my assumption is everybody will have done this already. I'm hoping that's the case. But the stuff I really want to talk about, as I've already said, is, so I'm only going to briefly talk about that. This is what stuff I really want to talk about. These remote sources of information that allow you to put this sort of information into a much broader context, a mine context or regional context fairly quickly. And they're not necessarily obvious. Like I think I said somewhere here, that you won't see a lot of YouTube videos about doing the remote sources of information or using them or in structural models, but you'll probably find lots of YouTube videos about measuring outcrops or direct measurement from drill core. So that's why I decided to focus on this. So the sort of bits of information that are really, really useful, particularly in the modern world, LiDAR DTMs or laser scans of open pit workings and underground workings. Geophysics, I've meant to reorder those, not that I'm picking on the geophysicists, but photogrammetry was the big thing about 10 or 20 years ago, 10 or 15 years ago, but it's kind of been supplanted a lot by laser scanning and LiDAR. There's borehole wall imaging, which I don't talk about much in this, optical televiewers and audio televiewers where they scan and image the walls of holes and they can put that into a 3D system and directly measure alphas and betas or directly measure dip and dip direction of features in the computer. There's aerial satellite imagery, just good old Google Earth. It's one of the most powerful tools that's become available for me in the last 15 years. And then geological maps, both old and new. One of the things I've talked a lot about in other talks is that there's no such thing as old data, at least in the mapping world and in mining, because so much of the record of mines that you might be interested in now might have been, some of those workings you're interested in re-accessing now might have been mined 50 years ago, particularly places like Rosebery and like places I have worked on, like Hercules here. The only information you might have about that entire mine might be on old linen plans in a shed at the back of the core yard. But just because it's old mapping doesn't mean it's wrong mapping. If you can get that registered in the GIS system, or preferably in 3D, which is where the space I work in, there's no such thing as an old map. It's just a map, and you get it in. As long as you can find reference points, you get it into the system, and you can look at it and get a lot of information out of it. Anyway, stuff I'm going to focus on. But I do have to mention orientated drill core, because this is what it all hinges on. Orientated drill core is basically, there's a lot of methods for doing this, but basically the most simple and probably still the most widespread is called the spear. It's basically a big pointy stick that you drop down the drill core, the drill hole. The driller does this for you. It spins down the bottom of the hole, and it basically hits the bottom of the hole and leaves a dent, hopefully in the bottom of the hole. And then when you over drill that mark and pull that stick of core out, you'll be able to see that mark and know that that was the bottom of the hole. And then you can consolidate all those different marks, and the driller does this on the rig, or the fieldies will do this. It's usually the technical officers in the core yard will find all those marks. They'll put all the core back together, line it all up, and they'll mark the orientation core, the orientation lines on the bottom of hole lines, join up all those different dents that have been put in the bottom of the hole by the spear or the other method, any other method, and they'll mark on the downhole direction, which is that sort of half arrowhead you can see on those black lines in the core tray at the bottom. So you'll know all through that drill hole where the bottom of the hole is, and if you know where the bottom of the hole is, all the other features that occur in that stick of core can be measured either using a goniometer or a canometer. So it's just one of those instruments for sticks of core, or you can put them on a rocket launcher, and you'll know where the bottom of the hole is. You can orientate the core, and off you go. So drill core orientation, it all hinges on drill core orientation. So what do you do with this typical sort of information? Well, this is the stuff I'm still, even 15 minutes into this talk, I'm still not going to talk about this stuff much, even though I have. But what do we normally measure? The sorts of planar features we measure are things like bedding. We also want to take a note of younging, nisosities, schistosities, flow banding, anything that is a planar feature that might help you work out more about the orientation of those rocks later in the project when you start interpreting things. Cleavage and crenulation cleavages tell you things about deformation. You want to know about faults and their orientation. It can be quite difficult to measure faults, shears, all these sorts of features. And then linear features like lineations and folds, the plunge and the plunge direction, and also the divergence, which I didn't put on this slide. You want to know about all those sorts of things. And the reason you want to do all these things is you can plot them up on stereo nets, which are not scary. The software has made these things so amazingly easy to use. And they're basically, they're kind of stereo nets where you take these are all discs. The different coloured discs are different sorts of geology. There's a legend in the top right-hand corner. So these are the alphas and betas from orientated drill core that are displayed in a 3D package. They're colour-coded by type, so whether they're bedding or a pyritic vein or a fault. And you can take that sort of information and put it into a stereo net and start to see the broader scale patterns of orientations of features of different types. But as I said, it used to be a real chore to do stereo nets. Now it's just a dream. The software just does it for you. So, generating structural data. So everything I'm talking about kind of from now on is not the more obvious stuff. So you can actually generate a data set very quickly just from taking a 3D a geological map. This is some work I was actually doing for the talk I'm giving tomorrow about Hobart geology at the forum. You can take the beautiful, in this case, 25,000 scale geological map of Hobart, drape it onto a LiDAR DTM or a DTM you create from drill hole collars or anything else that gives you a topographic surface in 3D. You drape the map on it, and then you can use, in this case it's Leapfrog, but you can do the same with Vulkan, the two main packages I've used and still use. You can generate in 3 dimensions, you can take the mapping, just the geological survey dip and strike measurements, and in Leapfrog you can create these structural data disks. In this case it's bedding in Permian rocks, Permian sediments, and within 20 minutes, if there's good mapping, you can actually generate hundreds of data points for an area. So I'd spent about half a day using the 25,000 scale mapping for all of Hobart to generate a structural data set for that. And you can just plot it up straight away as you go. You can actually have the stereo nets live while you're generating these data points. And it's just, I won't show you how to do it. You can Google how to do it from Sequent, and from Maptic. But basically, you're generating these data sets. In this case, it's all Permian sediments, and you can just, there's this running plot in the stereo net happening in the background as you do it. And in this case, if you know anything about the sort of patterns you get on a stereo net, in the bottom right-hand corner, it's a largely horizontal sequence. It's just slightly undulating bedding. But that's how amazing the software makes this stuff. So I've already kind of said this, but I did want to point out that most people seem to be pretty comfortable with iogas, and we've just heard from some people that are like the experts in this stuff, and we're probably going to hear from another one in a minute, not necessarily about iogas, but basically everyone seems to be happy with iogas and the amazing patterns it shows you in geochemical data. Well, stereo nets, as scary as they probably were in second year, are probably that they are just what iogas does for us in the geochem world. They just find patterns in different types of structural data. And the software, as I said, takes all the pain out of them, and they are the most amazing thing for just seeing patterns. So stereo nets are not scary. I'm already 26 minutes in. Right, so now what I want to talk about is, I just want to focus now on just a whole series of these less common, and I think maybe, please, I apologise if these things are really obvious, but not necessarily obvious sources of structural data. And these are the things I've already kind of talked about. LiDAR and photogrammetry. As I said, photogrammetry has kind of been superseded a bit by LiDAR, but it's still used, and there's libraries of amazing 3D images in some of the bigger companies that you can use. Geophysics, borehole imaging, which I don't talk about much. Aerial satellite imagery and geological maps. It's really just a repeat of that earlier slide. But then there's some even less, I think, obvious sources of structural data, particularly in a mining environment. And the ones you kind of get from drilling, which you may not think about. Maybe you do. I apologise if you do. We can talk about it over a beer later. But RQD data. I'll give you an example of using this in a few slides' time. There's drilling penetration rates, where the drill hole encounters water. And I'll jump this in now. And that's basically talk to your drillers, read the plods, put this into your database. If you suddenly encounter water, it might be the water table, or it might be what the old timers would call a water course. It might be a water-filled fault or something like that. So basically, that's why drill plods are really, really nifty because, and the drillers, I mean, if the driller's telling you that something's going on down hole, that it's bad ground, and he thinks he's running down a fault, or she thinks it's the ground is a void, then that's a note that maybe what Jane said earlier, don't put it in the comments column, find a column for that. Could almost be called driller's comment or something, but it should be in the plods. So yeah, so just listen to your drillers, but RQD data, like I said, I'll talk about that later. There's lots of other sources of information you may not think about, even though you see them all the time, and I think Dale might even show us an example soon. The sort of structural data you will see just by opening up the resource model or the block model, filtering it to show the high grade in the point cloud, and look at the patterns. And you are going to talk about that, aren't you? Yeah, terrific. And you'll see where the shoots are going if you've got a big old data set, especially one like an underground mine that's being developed below an open pit. If you get the blast hole data out and the drilling and the resource definition drilling for the pit, even though the pit's been mined out 20 years ago, if you have that data set, then you can actually extrapolate all the patterns from that data set down into the new area you might be trying to develop an underground mine into. And I must say, you need the structure for the wall rocks as well. There's underground sampling, like old-fashioned longitudinal sections, but it's just, these are old plans usually, but you can usually stand back and look at the grade distribution in these old plans. I keep calling them old. I don't really think they're old. They're just in old formats, but they're modern. They're just data. Open pit assays, mine plans, like particularly cross sections and long sections. I'll talk about long sections a bit more in a minute. I wonder if anyone here doesn't know what a longitudinal section is. Does anyone not know here that's in the room? You've all heard of a longitudinal section? Phew, that's good to know, yes. Thank God. Sorry, I didn't say that. Geotechnical mapping. Geotechnical engineers are, they can be your friend on a mine, and it's funny how often you walk into a geotech's office and they say, oh my God, you're a geologist, what are you doing here? We've never seen one in here before, and it's like the office next door. And it's kind of an odd thing that's happened, but geotechnical mapping, like I've already said, is a really powerful tool. Anyone that's building a structural model should know their geotechs pretty well. And there's geophysical data and geochemical data as well. We've already seen a couple of examples of geochemical data from Scott, the way it can be used to understand geology. He's a bit of a master of that, but it also shows you offsets in geology, which is structure. I've already said that. Be nice to your geotech. Structural data and fault modelling for underground geological mapping. So this is one of my major case studies. This is actually one of the ones I was allowed to talk about it's the Cannington mine, but I'll just a little bit of a rah-rah statement. I don't know if any of you work around mines. I'm sure anyone that works at MMG over here on the west coast of Tassie is working around a mine. And it's if you're trying to understand what's going on at depth below that mine, then underground geological mapping can be quite an amazing thing. But if you're trying to manage that mine as well, in terms of ground conditions, then geological mapping is your friend. And it's kind of the oldest tool of geology in mines. It started in the old days. It was the mining engineers used to, pick up a few geological points around the place or construct a cross-section, a sharp cross-section like that one I showed earlier, an old Bendigo section. But geological mapping is the most amazing resource because drill hole-based models are good. You can make them really good, but if you want to make them superbly good and you're trying to understand a mine, then you can take the geological mapping and it calibrates your models. You can actually see, instead of I think that fault's going through there, if you actually mapped it on the 10 level between X and Y northing, and you've got that, with pinpoint survey stations all the way down the drive, and you can put that mapping into your 3D model, you can calibrate those fault models and make them much better, and your grade models and everything else. Yeah, geological mapping is the most amazingly powerful tool, and just because a drive was mapped in 1927 doesn't mean that that isn't as good as mapping that was done in 2022. As long as you know the surveys and you can get it into 3D accurately, and mine grids are usually pretty long-lived. So anyway, rah-rah statement. So here's an example of how you can use it. So this is one of the levels of the Cannington silver lead zinc mine in northwestern Queensland. And this is a job I did a few years ago, 3 or 4 years ago now. This is an underground level, and these are the drill holes that were available with dip and dip direction measurements to create a structural model. So my job was to create a structural model for this mine so that they could manage the ground conditions, because it was an old mine now and the ground was becoming less stable and they needed to understand the faults more, and faults were being reactivated. They had a model, but it just wasn't based on very much. So this was the kind of situation throughout the mine. This is just a slice through one level when I started. So the only information that was really available was they had this mapping database that went back to the beginning of the mine, really, the early 90s. It wasn't particularly detailed until you looked at it very closely, but it was actually very detailed, and it was full of dip and strike or dip and dip direction measurements on big A0 plans, hanging up in verti plans. But they'd scanned them all. They knew they were going to use this stuff one day, so it's all scanned. So because it's on a mine grid, basically I put it into, in this case it was Leapfrog. The one mistake I made on this project was at the beginning, I didn't create a topographic surface for the floors or the backs of the drive. I just brought it in at the average RL for the drive, so it was flat. And that led to some minor inaccuracies in Z values for structural measurements later on. Anyway, that was just something I realised later in the project. From that mapping, and I'll talk about kind of what you can do with extrapolating between drives a little bit more in a minute. But you could actually take that mapping, and the first thing I did was to just mark in all the faults that the geologists had mapped over the years, over sort of 20 years really on this level. and then sort of extrapolate between where there's actually an underground opening and where there's information, where an obvious fault with a particular characteristic, like a certain fill, was outcropping in this drive and it's outcropping in that drive. You could actually make a fairly good assumption that it propagated through, and you could open up the drill holes and look at the drill logging, and you could see if there was a drill hole intercept here that had a fault in it that had been logged that was the same characteristics as here and here. You could use those drill holes to actually control your interpretation. Anyway, you could come up with these level plans of the fault systems throughout the mine. So basically in this mine, there's two major faults, dislocating faults, and there's a series of these things that are splays between them. They're called bird faults in this part of the mine. They're all named after birds. Then you could add all sorts of other information in from the drill hole database. In this case, I just used the RQD just as centroids of downhole intervals, but I'm not sure it was particularly effective, but I'll show you a more effective method of using RQD in a minute. Then you could open up all the drill hole intercepts where the geologists had logged faults through the years. A lot of them, because they're brittle faults, they're very difficult to measure, so a lot of them didn't have dip and dip direction, but it was just an added layer of supporting information for what the interpretation was trying to achieve. It's like a second or third opinion. And then from that, you could go through all the level plans where the geologists had mapped dip and dip direction for 20 years, and you could do that leapfrog exercise where you could actually create a dip and a dip direction disk for all the measurements that the geologists had created in the mine over the years. And you had to be really careful because sometimes they did dip and strike and sometimes they did dip and dip direction. So you couldn't just sort of do it automatically. You had to check every one. So it was a bit time consuming. But something as simple as that for 12 levels, it generated 3,500 structural data points of different categories of structure in a fairly rapid time. It was fiddly, and you do go a bit nuts sometimes doing this sort of stuff. You have to have a bit of patience, but once you've done it, it became part of the routine work of the mine geologists as they collected new mapping. It just got added in, so it was an investment in time worth doing because it just became the core of an ongoing kind of procedure, mapping procedure. So the geos just added new data as they mapped new 100-metre lengths of drive. But from that, I guess the really important part is you could take all that information and generate this quite detailed structural model. So fault planes, and this can be quite fiddly too, but basically you just take the disk that you've created and the information that the geologists have left you in their mapping and in the drill core where they've told you that a particular fault has a particular fill, and you can start to put together, you know that data point you've created from geological mapping at the top in the right-hand corner diagram is the same fault as the one there. You've got the dip in the dip direction, dip in the dip direction, and you can create these planar surfaces. I won't go into how you do that. It's just a very simple process of slicing the model very thinly and then just extrapolating the trends of some of these disks and then using the mapping and using these the orange fault surface interpretations to get the broader trends and to correlate between these smaller chunks to build up these big fault plane models. And then, of course, you can actually do the same for all the lithologies in the mine that you might be particularly interested in. And this, I haven't put them all in. This is just one. This is just an amphibolite body that occurs within this big fold system in the middle, big fold structure in the middle of the ore body. But you can actually do this to go back and calibrate all your litho models in 3D for the mine. And like I said, in a place like Rosebery, where you've got mapping going back to the 1920s, you could do, I think you already have, so, telling people how to suck eggs. But if you don't have this sort of information in a mine that you're working on or one you're planning on working on in the future, or you've got a historic mine in a brownfields exploration area where you have the data and you haven't put it into your 3D exploration model, then you can go and do these things. In Leapfrog and MapTech Vulcan, you can generate these things in a week, and it's a pretty good investment of time. Right. Now, one of the techniques that I've used far more than I should for almost my entire career is probably the simplest thing I ever read in Hobbs, Beans and Williams, which is the structural textbook when I was a student back in the 80s, early 80s, and that's form surface mapping. Now, I've got an explanation, so I'll just keep going now. Form surface mapping is basically where you're just using any information you can get. It's usually done at surface, and it's where planar geological features intersect the topographic surface and you can draw a linear line. So a geological form surface is just the trend of where any surface intersects the topographic surface. And in a 3D environment, they're the most amazingly powerful thing. And it's amazing what you can do with these things. And I've got a few examples of these things. I just pulled this picture out of a paper by Paul Dirks, who's up at JCU. It's just an island in the Arctic or the Antarctic. Just showing what form surfaces can do. They're a technique that was really developed in high-grade metamorphic terrains because it's so difficult to get any meaningful information out of stereo nets in high-grade metamorphic terrains. So if you want to actually understand high-grade rocks, you tend to map out the units like, in this case, it's an ultramafic, I think he's called it. And then you just do the trends and everything, and you actually get a really quite an accurate picture, a detailed picture of what's going on in these rock masses that have been multiply deformed and everything's just been squished. Although Paul does actually prove that the S4 fabric is folded. Anyway, it's another story. And it's particularly powerful, this type of method is particularly powerful in lots of mining environments, but it's particularly powerful if you're working in an area that I did work on in northwest Queensland. After I finished in the mine, I moved into regional exploration, where you're working on complexly deformed rocks underneath cover, but you have magnetics, aeromagnetics or something like that to work with. So here's an example of using form surface mapping to enhance your understanding of the regional structure surrounding a known deposit, and then trying to understand the controls on the mineralisation of a historic mineral field. So the figure on the right is the geological survey map, 1 to 50,000 scale geological survey map of the Hampton Consols area, which is a historic copper mining area in northwest Queensland, not that far from Cloncurry. But this is just an example of, this is what you get from the geological survey, which is a pretty good map, and these blue-grey features are all amphibolites. I didn't put the legend on, I just hope I'd remember to explain it. But the mine area is, if you can see the cursor is down here, and the way this map looks is it implies that the mineralisation is all along a fault. That's kind of true, but kind of not true. So if you add in the Google Earth imagery for that area, always high resolution, as high as you can get. Google Earth's pretty good for this. And drape it onto the LiDAR DTM, you get these kinds of images. Now, the LiDAR up in northwestern Queensland, the highest resolution you can get is 20 metres, which is not that good for the sort of work I'm talking about. But as soon as you put an image on it and you've got exposure like you've got around the Cloncurry area for a lot of it, you can do these amazing things. So I think they're amazing. So if you do the form surface interpretation of just the trends embedding, you can see everything from vegetation to the LiDAR to the geological map, which has form surface lines marked on it. If you combine all those different aspects of getting of linear form surfaces from all the different sources of information you can get, you can actually construct these very detailed maps of what the structures are doing, just like Paul Dirks did on that island in Antarctica. So this is all in outcrop area. But then you also, what's even more important in many ways, is you can see the offsets in the form surface trends, and you can start to mark in the discontinuities, the big fault systems. So the geological survey guys, they capture all this stuff, but you can really ramp up the quality and the detail of this. And this, I'll hopefully convince you why this is useful. So you can overlay that, and like I said, this is all done in 3D. For me, I mean, you easily do it in GIS. It's the same process, really. But if you can't move into 3D, you miss out on kind of the next step. These are the amphibolites, and the amphibolites there just outcrop as black, so you can see them quite easily in the aerial imagery. I have actually been to this site, so I've checked a lot of this stuff in the field. But if I zoom in on this area where the historic mine, actually is. sorry, I've suddenly leapt. This is the area of that red box, red rectangle that I just zoomed in on over here. So that's still a plan view on the right. And this is actually historic mapping of the jasper and the like the gossan that outcropped at this mine, the way it was mapped in the 1930s. A lot of it's been open cut since. But over on the left is, I'll zoom in on it in a minute, but so this is the plan view with the surface expression of the lode as a gossan and a hematite peruginized zone. And you can see the relationship of that gossan to the core of that anticline that we've sort of defined in the imagery, in the form surface mapping. But then if you start looking at it in 3D and start to add in the mine data, so these are the long sections from the historic mine and the underground mine levels, you start to see what the high-grade ore, the geometry of the high-grade ore in this deposit was doing when it was mined. And like I said, I think it was still mining in the 50s. So this is all done from paper. There's no drilling involved in this at all. The most modern technology involved in this interpretation is really Leapfrog Geo software and LiDAR. But these red shapes are a long section of the ore body where the old stopes were, but they're correctly placed in their position, in their true geometries, using the mine underground levels. And you can add in features of the geology that were only really recorded in cross sections. In this case, this doesn't show up very well, but that's an anticline defined by amphibolite. And this is a very deformed, probably body of amphibolite with a fault that's offsetting it on the eastern side. And it cuts through the workings, and you can see that fault plane in the workings. But all done from really quite old plans from 1950s, immediately post-war. But I mean, why does this matter? Well, if you went into this prospect and looked at the geological survey mapping, and maybe even what's been written about it, you might think, well, this lode is a lode. It's hosted in a fault system. But what this work showed is it doesn't show it well. Just didn't want to show 3D models because I was worried about the tech. But it's a saddle reef, effectively. So those stopes there and there are on either side of the hinge of that fold. I think I cut out the cross section. Yeah, I decided I wouldn't bother. But that, and this is all just done from the geologists from the 1950s and their interpretations. But you can go back and check this stuff. And there are drill holes for this prospect, but this is an open source project, so I didn't have access to any drill holes. I don't think the old drill holes have been put into a system anyway. But anyway, it turned out to be a saddle reef. That was the major control on this ore deposit. And what's really interesting is that the doubly plunging orientation in those stopes is an intersection of the structures and the amphibolites, I think. And there's multiple amphibolites in this sequence, in this fold. This is a parasitic fold on the limb of the bigger fold, but there could be repeats of that same geometry if any more amphibolites get into that structurally complex zone. So there could be lodes dropping out at the intersection of the structures and the stratigraphy, the amphibolite zones. And 12 minutes left, so I better hurry up. I'm going to really have to hurry up. This is an example from Cannington, which is a lead-zinc deposit, northwest Queensland. This is all undercover. So this is all based on geophysics. So this is the Cannington ore body. It looks small. So yes, yeah, I had to jump straight in here. There is a scale down here. That's 12 kilometres, I think. So just different sorts of geophysics that were available of the basement. This is all the mag that's showing us what's going on in the basement. If you take that and just interpret the basement using all the different variations of magnetics, not just the first vertical derivative or whatever, I use them all and the grey scales. You try and build it up. What's the best interpretation? So it suddenly gives you this very clear picture of the structural environment of that little ore body, which doesn't have a lot of satellite mineralisation around it. Then you can add in information from geological survey maps and imagery where there is actually outcrop from, so this is, like I said, that's all interpreted on the basement. You add in more information from the outcrop areas and geological survey mapping. You get a very detailed idea of what the fault system is doing. You can actually see that the fold geometries are becoming much, much tighter as you approach this major fault zone, which is the Cloncurry Fault. So you see what's happening there. So you get a picture for what the fold geometries are doing around that ore body, and that might lead you to be able to interpret where any mineralised horizon in these very complex rocks could be going. And that was kind of what the result of this was. Oh, there's the geological survey mapping. Now, you can add that into 3D and add in all the geophysical methods. Now, I'm a geologist, so I like to work with 3D models of inversion modelling. But you can add that into the 3D environment where it's all been done in the first place, and you can start to interpret the fault zones using the regional drilling. It's widely dispersed once you get away from the mine, but you can actually start to put in 3D models of the faults, and this actually led to a 3D seismic survey, but that's another story. So I'd put the Cannington ore body, even though it's completely undercover, between 30 and 450 metres undercover to the south, Cretaceous cover, put it into a structural context. And you can do this underground. The same form surface mapping works underground. So this is an example from the North Mine. This is one mine level of the North Mine, the way it was mapped in the 1970s, 60s, 50s, the 27 level. This is lead grade mapping. So it was done for mining purposes, for resource estimations and reconciliations. The geologists used to map the grade in these stopes. That's what Broken Hill's like. It's an amazing mine to look at, a phenomenal ore. But you can take their mapping and you can actually strip out all the structural information you want to actually help you understand the structure and how the ore body relates to the surrounding rocks in terms of timing, whether it's epigenetic, syngenetic, whether it's been deformed with the rocks around it. So this is kind of the information out of the original mapping that's been stripped out. So the way the geologists have mapped things like bedding and banding and the ore body boundary itself. You can interpret, you can extrapolate some of those trends where you think you've got reasons to get creative sometimes about where you think the bedding is going or the banding is going, and you can actually come up with these much more detailed plans of what the folds are doing. You can do the same in the ore body, and in this case, the ore body had a fabric defined by galena in the ore body itself. So there's a structural fabric in the ore body. The ore body had a foliation in it defined by galena, and that's really common in ore bodies. You don't read about it much. But it tells you that that fabric there is probably actual planar to all these complicated folds that are trending in the same direction. You could add in the later shear zones and the cross, oh, I must have deleted that slide. And the reason that it looks a bit wobbly is because it's all been hit by another overprinting generations. Should be a slide with F4 folds trending that way. Sorry, it must be hidden behind one of those. And that's the original mapping in the bottom right-hand corner. All this information has been extracted from mapping that was never intended to be used for structural geology. And at Broken Hill still, this is just a different part of the mine area, but what really came out at Broken Hill was that you could use these form surface trends and their truncations to identify high-grade shear zones that you wouldn't actually ever really identify underground because the rocks kind of look a bit weird, but they don't look like they are particularly deformed, but they are actually rocks that are intensely deformed, but at high metamorphic grades. So there's shears. They've been reorientated and almost plastically deformed. But you wouldn't recognise those unless you could see the truncations in the form surfaces. You can do the same sort of thing with grade mapping. I'll flash through this because it's not the same thing, but if you map out the gangue mineralogy in this intensely deformed ore body, if you use a bit of an eye of faith, this is where the quartz gangue is, the fluorite gangue, and the rhodonite gangue, which is a manganese pyroxenoid, very common at Broken Hill. But you get the impression that the folds are overprinting the geometry of those gangue minerals, and they are probably an early layering inside the ore. And this sort of information helps you to know whether your ore body has been deformed or massively moved up in the fold hinges, which is one of these myths you always read about. Folds are full of ore that have been shoved up into fold hinges. I'm sure that's been said a lot here at Rosebery, and certainly was at Hercules. But anyway, if you map out the gangue mineralogy, it can tell you an awful lot about what goes on inside an ore body. Ore bodies are rocks like any other rock, and they have structural fabrics and structural histories and metamorphic histories like any other rock. But nearly every section you see of a mine, the ore's coloured in black, and all the exciting stuff's going on in the rocks around it. Well, it's just not true. Anyway, and you can do this sort of thing at cross-section. This is another Broken Hill example. This is an old shaft section, and I just decided to see if I could make the folds make sense. And you can do this section after section at Broken Hill, and you can see that these things are probably real. So it's just a great way to work out the deformation, or the geometry of deformation of folds in particular, and shears and faults in these high-grade rocks. Now I'm going to flash through these. This photogrammetry has pretty much been replaced by LiDAR and laser scanning in mines. But in this example, which was in northwest WA, they had this massive photogrammetry database that went all the way back 10 years, at least 10 years. And what can you do with photogrammetry? If, in this case, these benches are 15 metres high. You can, and these are also 15 metres high, you can actually do maps, form surface maps, kind of. These are actually just, I call them skeletal maps. You can just pick out all the relevant features you want, which are red are faults, blue are green are joints, white is bedding, and then there's some other bits and pieces that pop up as well. Yellow are shale bands. But you can use this sort of information to massively increase your data sets, particularly in open pits, if you're in a big mining operation. So this is an image of one of the satellite operations up there where I was working, where it showed the mapping that we had at the time. But we didn't have a lot of structural data. There'd never been a lot of structural data collected out there. So I went back and accessed the photogrammetry archive, which had still been collected. So I started to do these mapping interpretations, just like that earlier example, the skeletal map, from all the satellite pits, added all that in. That was the structural data that we had from the old mapping and the surface mapping, but it didn't have a lot of information about faults. That's what the existing data showed us. It was just pretty much a flatly dipping bedded sequence, but basically went back and mapped as many structures of different types as I could from the photogrammetry and identified this quite major fault system that was parallel to some of the walls. So basically, even though I'm flying through this, the photogrammetry allowed a whole new data set, over 300 structural measurements to be collected from photogrammetry archive. I think it was a project that took 3 days to generate 300 structural measurements and the mapping as well, the skeletal mapping, and identify this new fault structure in the high wall. Now, I'm not going to talk much about photogrammetry. It has kind of been superseded, but I did want to use this slide. This is from Adamtech Imagery. You can take these photogrammetric images and the laser scanned images and do these geotechnical analyses. You can actually, they have processes in the software where you can click on a surface in the image with that orientation, and the software will go and find all the other surfaces in that image with the same orientation or within 10 degrees or whatever. And you can generate massive data sets about joint systems using these kind of software packages. So whether they're flat tipping, vertical tipping, or any other trend, the software will go and find them for you. But you can also map them yourselves. And you just generate the discs, very much the same as I showed you on that Hobart 25,000 scale map. And you can do them in underground workings as long as you've scanned it before they shotcrete everything and ruin it, or in open pits. Yeah, you need those 3D images before shotcrete. Luckily, I'm not quite sure how many slides I've got to go, too many. You can take highly detailed LiDAR. 1 metre LiDAR is the best, although it makes your computer have problems in working with it. Drape an image over it, and then you can carry out these sorts of form surface interpretations. But LiDAR is the most powerful tool for generating new structural data, especially if there's an outcrop area. Now, it's an amazing tool that we have. So much of Australia is covered in 20 metre LiDAR, but the whole island of Tasmania is covered in 2 metre LiDAR. You can just cut and paste any bit of it you want in 2 metre. If you're in a mining environment, you can get structural data from CMS surveys. This is a CMS cavity monitoring system survey of a raise bore that had a lot of problems in its footwall. This is the structural model. This is Cannington. I generated this model, and then the geotechs took the model and compared it to this area they were having problems, and they came back to me and said, well, your model's pretty good because it's told us what that problem is. But you could actually take this model and generate planar structural fault models from it and feed them back into your structural model and calibrate the model that I generated just from level mapping. So these CMS systems will give you information in the footwall and hanging wall of voids. I've talked a lot about geophysical data, but this is just an example also from Cannington. It continues on from that work I did, where I'm a big fan of these inversion models. I like to see geophysics look as much like as possible like geology. Sorry, I'm a geologist. But this is where we were trying to understand this big fault system that continued south of Cannington. So my colleagues at GeoDiscovery did a lot of these inversion models of geophysics, and we used them to actually try and constrain this big fault system that heads to the south of the mine. And you could really see the differences in the geology on either side, just the geometries. We're not trying to find ore bodies, we're trying to understand the geometry of the rocks that host the ore body. And anyway, he ended up developing this quite detailed fault model, which ended up forming the framework for a seismic modelling, 3D seismic program. And then off we go. Now RQD, I'll just go straight to the image that really counts on this. You can take RQD data from drill holes, create centroids from the intercepts, or create a block model, and then you can contour them up. This is just isosurfacing values of from 0 to 50. But in this case, this is a mine level where there's a major fault here. There was a series of splays identified in the footwall of that fault, which were known about, but this interaction area here, the footwall damage zone, was much wider. So the RQD just allowed us to pin that down and show the relationship between the footwall of this major fault and these splays that were well known, and all through the mine. You can do the same with blast hole data clouds. This is an old model that I got from Savage River a few years ago now, nearly 10 years ago probably. And you can just use blast hole data to identify the chutes at 5 minutes, or am I finished? 5. Right. Anyway, just more of the same. But so you can use your blast hole data to get an idea of what the geometry of the high-grade ore is doing in mined out areas, but you can use that to understand mined areas, future mining areas. And this is what I was going to talk about, long sections. You can actually extrapolate between those areas and ask yourself the question, why wasn't this area ever mined? It might have been mined, it's just not recorded. So you might want to drill. If you're in an old historic mine and you get these plans in, you could drill these areas and there might be ore there, as simple as that. But you might, it also tells you the plunge of the high-grade ore. And you can actually use these types of plans to build up quite sophisticated mine models that show what all the different stopes were doing in a mine. This is just one I did from open source data at Clunes in Victoria. So this is a saddle reef in Victoria. I visited the site and just thought I'd see what I could do with the data that was available. I won't talk about seismic data, except it's probably one of the most important tools that we have for monitoring what's going on in the walls. So what's some of the problems? These are getting towards the end. Sorry, this is taking so long, such a rush. Structural data hinges on the orientation marks. So if you've got the problems that you are likely to encounter with structural data are likely to be the problems with the orientation data. So you need to understand the orientation data really well, and you need to monitor it at the rig, which is one of the things we've already heard. For accuracy, consistency, and the method used all need to be documented. And the other big thing that really counts for structural data from drill holes is to make sure that you've got the good XYZ coordinates, particularly the Z, the RL, the height, the altitude of the collar. If the collar's out, and they quite often are in holes that you might have inherited from regional drilling, regional exploration drilling, you need to fix that to make sure you've got accurate RLs. Otherwise, structural measurement you take, if you're using it for an interpretation, is going to be at the wrong level, let alone X and Y. They're pretty self-explanatory. And if you're getting long runs of broken core, it's almost impossible to orientate core. And it's also very hard to get decent structural measurements in broken ground because you just don't have planes you can measure, big broken faults. But anyway, some of the, I think I'll leave this for you to read through when you review this. But some of the problems that I've encountered the one that really surprised me is that you'll find that on a mine, and even in exploration and feasibility teams, structural data is being collected by a lot of people. And it might be hidden away by the hydros, or it might be hidden away by the geotechs, or it might be hidden away by the mining engineers even, or the exploration people. It's not the same database, may not even have the same coding system. So the trick is to get it all into the same database from the very early stage of a project. And if you take over a project or you're working on a project, it's always good to go and talk to all these teams to see if they find out if they're actually collecting this sort of data. And do you know about it? Because if the danger is you could go back and relog 50 holes that have already been logged by the hydros. And what a waste of time and effort that would be. So I won't talk too much about the software problems, but I'm sorry I've raced through that. But like I said, the lists are there to review. So just pause this if you want to go back and read it. But what I've tried to do here is show you about all the stuff you may not find out about in YouTube videos. So you'll find out about alphas and betas and drill core orientation and clever ways of generating data in Leapfrog. But these sorts of things, I just wanted to make you aware in this rapid talk about all the other things that you can use to put those drill hole points into a broader context of a lithostructural context across a region or within a mine. There's so much other information you can use. So that's kind of what I've tried to focus on here. And the last thing I'll say is that we've heard a lot about having perfect data sets and all the things you have to do to make them perfect. But I think when you're working as a project geologist on an early stage project where you might be putting the data together, it might just be better to just get it together and understand the architecture of the system and then move on. And fix the data, make sure the new data is great, and then fix the older data up as you go. But these sorts of methods I'm talking about are a great way to get the architecture into the model as a framework to build on in many ways. So the trick is to just get it in, but be aware of all these other sources of information, particularly if you're working in a brownfields area like the West Coast here.